Okay, so for this video, we're going to talk about how to graph a square root function when it's kind of in transformational form, and we'll connect it to using AH and K in the problem after we've just kind of talked about it conceptually. So if I have g of x equals the square root of x minus 2, remember that I want to strategically have my radicand, so the expression inside the radical, be perfect squares so that I don't have to use a calculator to find the values. And so if I want that x minus 2 to be perfect squares, the perfect squares that we want to use are 0, because 0 is the first number that I can take a square root of, right? I can't take the square root of -1 and graph it on a coordinate plane because that has an imaginary answer. And so I want to kind of force my radicand to be 0. So I'm thinking about what number minus 2 is going to make 0. And so that number is positive 2. And so if I think about this, if I plug positive 2 in, the square root of 2 minus 2 is 0. Okay, so that means that when x is 2, the y is 0. The next perfect square is 1. So I want to think about this in the same way. So what number minus 2 makes 1? And so 3 minus 2 is going to make 1. And the whole point of that, again, is that if I plug in 3, 3 minus 2 is 1. The square root of 1 is 1. And so that's going to give me a y value of 1. Finally, I want to use 4 because 4 is the next perfect square. And so I'm thinking about what number minus 2 is going to make 4. And that number is 6. So if I plug in 6, I know I'm going to get 4 inside the radicand. So 6 minus 2, again, is 4, just as I wanted. The square root of 4 is 2. So what this means is that the points for this graph are 2, 0, and then 3, 1, and 6, 2. And so the graph of a square root function always looks kind of like a parabola going sideways. So we have the sideways half of a parabola. Because of this shape, if we think about the domain, the first number that I used is actually the first number that I'm allowed to plug in, because we talked about if I try like as a 1 minus 2 is negative. The square root of a negative is imaginary, so that has no real solution. So my domain is x values such that x is greater than or equal to 2. So visually I can see that my graph starts at 2 and keeps going on forever in the direction to the right, so it doesn't move to the left. If I would prefer to write that as an interval, that's the interval from positive 2 inclusive to positive infinity on my x-axis. The range, looking at the values from the bottom to the top, notice that the first y value that I have is 0, and then it's increasing. It's not increasing very well, but it is increasing, so it will eventually get to infinity vertically as well. And so that means that my range is also a greater than or equal to value. And so the range is y is greater than or equal to 0, because 0 is that first y coordinate. Again, if I prefer to write that as an interval, I would write that as from 0 to infinity. So my graph starts at 0 vertically, and then it keeps going on forever, right? So my graph will increase forever in that direction. So because as x gets bigger, y increases as well. So as x increases, y increases. Or we can think about this as the slope, if we can call it that, is positive. That means that this function is increasing. Okay, so as we visually see from left to right, the slope is increasing, not at very large increments, but it is increasing. So if I connect this kind of back to AHK form, so if we look below here, we have a reminder of if I have a radical, and notice that this has an index of n, it doesn't matter what that index is, that A is the number in front of the radical. So if I multiply by A, that determines a vertical stretch or vertical compression. H determines our horizontal translation, so it's moving it left or right, and K determines a vertical translation, so that's moving it up or down. So thinking about that form in the equation that we have here, in this equation, we can think about it as it having a 1 in front and a plus 0 at the end. So that means that our equation has an A value of 1, an H value of 2, because it's 1 minus 2, and a K value of 0. Let me make sure I did those colors correctly, yes. And so that means that this function, we can think about it as the square root function, really just translated to the right too. So visually we see that. One kind of connection to make is that our H value was 2. Notice that was also our first X value. And then our K value was 0. Notice that was our first Y value. And so that is actually going to be the case every time because we're trying to get 0. So when I'm trying to get 0, that's what's happening to our radicand, and so we're only left with the K value. So when I'm making my table, instead of thinking about it as what minus 2 equals 0 like we did in the problem, what we can think about it is that our table is always going to start at H for the X, and it's always going to start at K for the Y. So this is going to be true for every table that we make. In addition, what you can notice is that our original values that we used if we're graphing the parent function were the numbers 0, 1, and 4. And so what I'm technically doing for the first one is I'm adding 0 plus H, and that gives me the value. The second value is always going to be 1 plus H, and the third value is always going to be 4 plus H. So again, if I think about this, 0 plus 2 is 2, 1 plus 2 is 3, and finally 4 plus 2 is 6. And so, I mean, if you think about the expressions that we wrote with the question marks, all we would do is add 2 to both sides to get what the question marks are equal. And so that pattern's always going to be the case. So if I remember that for each of them, that's a strategy where I don't have to think as hard about, okay, what makes 0, what makes 1, what makes 4. I'm just adding H to those values that I want it to be. And then the pattern for Y is a little bit different, but it is pretty straightforward. In this part, to get the next Y value, I'm adding 1, and then I'm adding 1. And if I look at my values A, H, and K, I'm actually adding my A value each time to get the next Y. So that means that I'm going to take and I'm going to add A to get the next Y value from K. And I'm going to take and I'm going to add A to get the next Y value from K. So that doesn't mean that I have to use this pattern to create the table, but it is a nice connection to make things easier if I'm good at memorizing and identifying these patterns. Another thing to look at is our domain and our range. So notice that our H value and our K value appeared there as well. So our domain included our H, which was 2, and our range included our K, which was 0. So our domain will look like this every time, as long as we don't have some kind of reflection. So remember that if I'm multiplying something by a negative and I have a reflection, the direction of the inequality can change. The values will always be H and K. So my domain could be X is less than or equal to 2. My range could be Y is less than or equal to 0, and it's going to be dependent upon the visual, which has to do with our A. So if A changes, those values can, or those inequalities can change. But in general, H and K and A are connected in that way to our graph of a square root function.